Okay, I'm going to do a little bit of a review with polar area. I know some of us were out Thursday, Friday. And also, in the interest of time, I'm just going to check the remaining pages of your homework on Wednesday. Okay, so Wednesday, I'm going to just flip through your entire packet. That way, I know some of you guys are still trying to catch up, but Wednesday, hopefully that'll give you enough time to catch up with the problems that you have. And if you're a little behind, I'll check up to page 68 on Wednesday. Okay, any questions there? On page 50, we did do number 3, right? Did we do number 3 on page 50? I want to go over this. Let's see. Yeah, I want to go over this problem over this one again, because I think there are some, it just feels confusing in terms of like, how do we know where the graph is and our shader region. So I want to try 53 again. Sorry, page 50, number 3 again. Let me present it a little differently here. Ultimately, area inside a curved region or polar region is not top graph minus bottom graph. It's all these sector regions that we're accumulating from the polar zero out. Okay, so they're kind of radiating out. So with rectangular graphs, we're adding infinitely thin rectangles, but here we're adding infinitely thin, these kind of pizza wedge sectors from one end to the other. So what I like to, for number 3, we realized that the intersection was, that's an important point, right? It says to find a common area of the region of the 2 polar curves. So we have a circle and we have a cardioid here. And so the shared region is the overlap between those 2 graphs. And the important thing is that there is going to be some shift after that point, right? There's going to be a shift after that point. Print it out, a larger version for me to demonstrate. And we know that if we want to find the area of this shaded region, it's made up of 2 components. The first component is having to add up the area that involves the circle, but we're basically doing this. We're accumulating all these infinitely thin up until that dotted line. And then after that point, at or hitting the cardioid. So imagine all these infinitely thin sectors that are hitting. So we're basically having to think of it as 2 separate problems, and we're just adding up the areas of those 2 regions. I think it's helpful to just well, first off, let's find that intersection, right? So the intersection of those 2 curves is where -6 cosine of theta is equal to 2 minus 2 cosine of theta. If we combine like terms, we get -4 cosine theta is equal to 2. Cosine of theta is equal to -1/2. Theta is 2 pi over 3 and 4 pi over 3. Now, we really want to take advantage of symmetry here because technically this is only half of the intersection, right? There's also this bottom half. But a lot of these polar graphs have symmetry. We really want to take advantage of symmetry because if we don't, then we're extending our problem and we're having to find areas of other regions that we don't have to, especially if we can just double what we already found. So we know that there is a critical point here at 2 pi over 3. But the issue is that we may assume that this is starting at some point on the curve for a theta value, but it may not be the case. So I think the best way to do it is let's just treat these like two completely separate problems and on two separate graphs, and we're just adding up this region and adding up this region, and in the end we'll sum up our numbers together. So I think it's to our benefit to do this, where we are creating a table of values for each graph so that we know where our graph starts and have an idea how it's moving. So if we start off with, let's say, the circle, for instance. So circle is r equals -6 cosine theta. That's my circle. And if we start off with theta 0, my bad. Independent variable is theta. I typically do theta, comma r. So if we start off at 0, what's r going to be? -6. So my circle is starting over here. Okay, it's starting here and it's moving in a clockwise, counterclockwise, counterclockwise direction. Let me just pick off an easy value here. If I pick off pi over 2, what's cosine of pi over 2? 0. 0 times -6 is 0. And then at pi, it's back to what? 6. So it kind of gives you an idea how the graph is moving, right? This circle starts here, and then at theta at pi over 2, it gets to here, and then at pi, it gets back to that -6. Right? So it's good to kind of have, to kind of know where our graph is starting, because if you look at the circle, you may assume that theta equals 0 starts here, but it doesn't. It starts over here. So it's helpful to kind of anchor our knowledge of how the graph is moving to begin with. Okay. Now, second, cardioid. Which is r equals 2 minus 2 cosine theta. All right, so let's start at theta equals 0. What's this going to be? 2 minus 2 is 0. Now, the cardioid does start here at 0. So this is that. So, our assumption is that everything's going to start here, right? But it's not, right? Circle starts here, but the cardioid starts here. Okay. Let's see here. Pi over 2. Cosine of pi over 2 is 0. 0 times 2 is 0. 2 minus 0 is 2. So then at pi over 2, the cardioid gets up to this point. At pi, cosine of pi is -1. -1 times -2 is 2. 2 plus 2 is 4. At pi, it gets to the halfway point. So not only does the circle and cardioid not start at the same point, they also have different lengths of their cycles, right? Circle is going to complete its full cycle from 0 to pi, but the cardioid is only going to complete its half a cycle at pi. and then it takes another pi in order to get back to a starting point. All right, so I think that's what's confusing. If you're seeing two graphs, you may assume that they both started at the same point at theta equals 0, and that they both have the same cycle, which they don't. So I think it's the easiest way to do this is treat these like two completely separate problems. Find the area region for one graph that you care about. Find the other region that you care about for the other graph, and then in the end, you'll just add them up. So don't think of it as one graph. Think of it as two separate graphs. I find that to be easier to less confusing. Okay, I think it's less confusing that way. So back to the circle here. If I want to find the circle starting here, we know that the circle is not going to hit a polar 0 until pi over 2. So then the circle portion is going to be 1/2 integral from pi over 2 to pi over 3, because we see that that's where our circle portion is going to stop. And then r squared d theta. Plus, okay, we have the green region figured out. And now the other one is the cardioid. We know cardioid starts here. This is at theta 0, then goes to pi over 2, and then to 2 pi over 3. And then from 2 pi over 3 to pi is where our cardioid region is going to be. So 1/2 depth integral from 2 pi over 3 to pi, and then r squared. And then after that, we just take all that and multiply that by 2. Right? Because after everything is said and done, we know this is only going to get us half of the shaded region, because there's also this other half as well, but we only need to figure out that half. So I think based off the questions that I received after lesson on Friday, I think that was part of the confusion. It's like, how do we know? Why does it not start at 0 for 1? And why does it not just continue? Why does it start at pi over 2? And I think, yeah, treat them like two separate regions, two separate graphs, and map out where your graph is just in terms of, not all the points, just enough where you know where it starts, how it's moving, and how long it takes us to finish the cycle. Okay. Page 53. Let's try number 7. So inside a circle and outside the other one. R equals 1 is simply a circle that is centered at the polar 0 with a radius of 1. And then R equals 2 cosine theta is just a circle with the diameter of 2, and it's going to be symmetric about the x-axis. So it's going to be at 1, or when theta is 0, it's going to be at 2, which means the center is going to be at 1. So it's going to have that overlap look about it. Okay, I want to find the region that is outside R equals 1, but inside the R equals 2 cosine theta. Let's find the intersection between these two curves here. And if we can kind of just have an idea where these graphs start and where the graph ends. So for R equals 1, 0. Okay, so this is pretty straightforward, right? So the circle is going to take, R equals 1 is going to take 2 pi for it to complete its cycle. Let's see. This is R equals 2 cosine theta. Okay, for R equals 2 cosine theta, we're going to complete a cycle at pi. It's going to be at -2 here, pi -2, which is back to where it starts. So if I just split this up here, if I want to find the area of that outside region, I first have to figure out the area of this region here. Which is basically the entirety of that 2 cosine theta. And then I can subtract out that inner circle portion. I just want to do the top portion here because I know that if whatever area I find ultimately in the end, I can just double it at the end here. So really, the hard part is just the setup, right? Because once you get to the setup, the rest of it is calculator, and then just make sure if you only have half the region, you can double it. If you double it, then you have your area. Okay, so try that, see if you're able to get that answer as well. Also, you can be in rectangular form. You don't have to have that theta show up. You can just use x's. Unless you're graphing it, you don't have to be in polar form. Yeah, 1.913. Multiply this by 2. Which, if you want, you can just cross off that 1/2, and then not, and then just know that if I double it, the 1/2 just goes away. Okay, I'm just going to pick out problems for us to try here. Page 60. Or 59. 59, number 5, but this problem stretches to A and B is on page 59, but then C and D are on page 60. Let's see if we can go through this one together, or try this. Yeah, this is pretty similar to the one we just did, right? Let me know if that's what you guys got too. Oh wait, hold on, I messed up. Sorry, seven. My bad. 7.653. Nice. Got to square that. Okay, flip over to page 60 and try part C and D. Or sorry, part C. There's no D. All right, again, it's pi over 3, not pi over 2. Pi over 3. Okay, so here's my strategy for this problem. The only part of the problem that's really giving us any trouble is that first and fourth quadrant, right? Because the second and third quadrant are just it's just a semicircle, right? So a semicircle, you just use 1/2 pi r squared to get to that region. It's only that this region that we have to figure out how do we get to this area region. So why don't we find out the area of this entire region first? That portion is 1/2 integral from pi over 3 to pi over 2 of r squared, which is this circle centered at 0. So are we in agreement that what I have in green is that shaded region there? Now I want to subtract out this region that is touching the other circle. I'm going to subtract out the brown here. And that region is 1/2 integral from pi over 3 to pi over 2 of 4 cosine theta. Okay. That's good here. So if I take my entire green region and subtract out that brown region, then what I have left is that shaded region that I'm really after. And if I can figure out that part, then I can just double it for that fourth quadrant that I see. And then you could do the integral of the third and fourth quadrant separately, but you can also just use area of a circle to get to that value. But yeah, you could also say the depth integral from pi over 2 to 3 pi over 2 of 2 squared d theta, and that'll get you the same thing here. Yeah, actually gives us the same answer, right? 7.653. Yeah. Why did we what? Oh, oh, you got a negative number?
Yeah, I did it wrong, but I was just wondering why it doesn't work the same way we did for.
When I say something wrong,
Yeah, go ahead.
is I noticed that for radius of two pi, r equals two only goes around the circle once, but r equals four cosine theta goes around it twice. So like any value, like, so I did do it the same way, but I had to go for r equals two to be pi thirds to pi. But four cosine theta had to go pi thirds to pi halves. Is what I did because I had to like how far it went.
Okay, so I think the additional complexity is um, that they're both going in different. They both take different lengths of time to complete their cycle.
Yeah.
So that's. So I think, yeah. So I think it's best to just focus on the smallest interval possible, just to reduce the amount of complexity that could occur when you have to involve um, um, yeah, especially when the graphs are not aligned in terms of their cycle. Yeah, I think that's the tough part. Um, see if I can pick up some more. How about number 11 on page 64? 1 and 2 both represent the portion that's, yeah, so both pi over 4 and integral from 0 to pi over 2 of cosine squared d theta. They both represent that inside circle that you're going to subtract out. Okay, spend about 5 minutes, just see if we can do a little bit of the practice problems, starting on page 55. Slope of the tangent line of polar is similar to what we do with parametric. We have to have our y component and our x component. We have to take the derivative of both of them, and then we evaluate them at the theta that we see. I think this particular problem is meant to be non-calculator, but you'll get to use your calculator on the test. But yeah, see if we can go through the whole process of product rule to build out your dy d theta and your dx d theta. So this one you can bring it down. I will do the first one. The first one. So I'm gonna check the rest of this book. No place. Okay, so tonight, if you guys can just focus on trying to catch up if you haven't caught up with our homework assignments here. But otherwise, you guys can make progress, page 54 to 60, but I'll check your packet on Wednesday. Tomorrow, I'll give you the test review packet. We'll start working on it. We'll have 2 full days to just dedicate time to do our test review. But your test won't be until next Tuesday because we're going to start 10.1 on Thursday. All right, come get your phones. What's that? Second. So one of the sounds kind of something. So you go to bed. Nice. It looks like this. 8 usually. Just make it less of a condition.
Usually 10:30 to 11. I'll wake up at 7:50. Sometimes I'll get up at 6:30.
I'm sure I'm birthday.
Anyways, I'll always.
Yeah, that's
an hour.
like that. No, that's great.
Yeah, even on the weekend. On the weekend.
Yeah, I saw on Friday. I'm not that great.
When do you get up on the weekend? When do you get up on the
I'm
weekend?
on chapter 15 right now. I haven't like.
Whoa, okay.
Yeah, we have one. Yeah, and it's really.
When you go to bed?
I'm really short. It's kind of. Yeah.
When you go to bed?
It makes me motivated to read. And actually,
It's all. Yeah.
Oh, yeah, it's good. Yeah, it's not hard to understand. It's not very like, yeah, like. Yeah. Yeah, right. Oh, well.
Yeah, I don't know.
Yes.
I feel like shit.
I'm sure you do that.
Like, what am I doing in my life?
Oh. Probably. It's like,
8:30.
Have a great day, guys.